Okay, in this video, we will try to continue from the previous video. We already talked about the motivation of this paper, and then in this video section, we will try to discuss about the detail how this algorithm of mClock works. Okay, as we already talked in the previous video that fixed resource allocations can do only change when the VM entry or VM exits. But in this mClock, in this case of I/O fluctuating resource availability, we need continuous monitoring. And this mClock algorithm, it uses this tag-based scheduling with three components. The first component is tag assignment. The second component is tag adjustment, and the third is request scheduling. And we'll try to talk about the detail later. Okay, in this case, we will have three tags. The first is reservations. This corresponds to the minimum lower bound. Okay, and then the proportional tag P here corresponds to the tag between the minimum and also the maximum. And then from the limit here correspond to the maximum or upper bound. Okay, let's try to discuss one by one. Okay. This is the pseudocode of the mClock algorithm. I think this pseudocode looks very simple. Okay, we have this one element, second element, and then third element here. First, second, and third. We have this. Okay, first, this is the second. This is the third here. Okay, we will try to discuss one by one. We will try to discuss the second component first. Okay, and then followed by the third component, and then we go back in the first component here. Okay. Okay. How we can do this tag assignment to ensure that this algorithm can satisfy the minimum requirement, the proportional share, and also the upper bound of these resource allocations. Okay. It has multiple real-time clocks, which are reservations, proportional, and also limit clocks. Three clocks here. Okay, and this is the formula in the previous pseudocode. For example, I only show the reservation tag here first. From the limit tags, it will be similar. Okay, so the formula is from the current request, we will take the maximum of this first term and also this current time of the clock of these reservations, because this is for reservation tag. Okay, and this is the previous one, this is the current one. Okay, and this is the gap or spaced interval. Okay. Okay, next. I need to clear this again. Okay, this is the first case. We will try to see how we can compute by using this formula. For example, this one, in this first term here, we have this number 10.3. Okay, and the current time of the clock here, for example, is 10.5. This is the current time of the clock, 10.5. And because of we have like only a small number of requests, so that we have small number of this, because every time we have requests, we will add this gap interval, and in this case we only have a small number of intervals, so that the increment of the gap is also very small. So we have the relatively small value here compared to the current time. And then we choose the maximum, and the maximum is this current time here. This is the first case. And then from the second case, we have many requests. Okay, in the case 2 here. Okay, so the first number is bigger because we have, for example, 1, 2 until 8 gap interval. Okay, so we have a bigger value here. And then in this case, this value is bigger than the current time. So we choose this maximum, which is this number, and we output this one. Okay, so what we can conclude for these two cases. Okay, so tag Ri, if the tag Ri is lower or equals to t, it means that the reservation value of the VM I is not satisfied yet. Okay, so in this case, the reservations, the lower bound of the VM is not satisfied. It is not satisfied yet. For example, if we have like VM1, VM2 in the host 1, okay, if this we have like a reservation, proportional, and also the limit. So the minimum requirement, the minimum requirement of this VM1 is not satisfied yet if the output of the RTAG is the current time. Okay. For example, if from VM2 here has the case of 2 here, and the output is the first term, so the minimum requirement of reservation here is already satisfied. Okay, so this is what we can conclude from this reservation formula. Okay, next we will try to discuss about the request scheduling. So after we update all this tag for reservation, limit, and also proportions, in the previous slide I show you only for reservation calculation. For the limit and also for the proportional calculation, it is they are similar. Okay, and next, after we already process all this tag assignment here, we will do schedule requests, okay, correspond to this third component. Okay, how we can do that? For example, if we have this queue of requests, okay, this is from VM1, request 1 from VM1, request 1 from VM3, request 1 from VM2, request 2 from VM2. The first is there any VM I with the reservation is still lower than the current time? It means that for the VI, the reservation value is not satisfied yet. Okay, for example, I have like VM1, VM2, VM2, VM3 here. This is host 1. Okay, for example, if the request from VM1, the R value is still lower than the current time, so it means that this VM1 for the lower bound is still not satisfied. Okay, in such case, we will go to this process, which is process IO request with the minimum of Ri. Okay, so in this case, we will try to fulfill the minimum requirement, the lower bound. Okay, let's say after we process all the requests, so that there is no VM having R lower than or equal T, we will go to these conditions. Okay, we will go to this wait-based phase here. We will try to process IO requests with minimum tag value of PI, and Li is lower or equal to T. Why this condition? Because if we have a condition of this, it means that the VM is still not beyond the limit value. Okay, so if we have L1 over than the T, it means that that VM is already goes beyond the limit value, beyond the upper bound. So we will not process the request from the VM. Okay, so this is the meaning of these conditions. Okay, and then why do we choose the minimum one? Okay, I will try to give illustration here. So consider if we have like VM1, VM2, and VM3 here with share of 100, 200, and also 300, and let's assume that the tag value in the previous are same for all, denoted by PR-1 here, and bigger than the T. This is just for example, and this is the formula. Okay, and then the P tag will be, we can calculate this one, and we can compare these three VM because this first term is same for all. We can just remove them for the comparisons, and because of we have this proportional value here, we will try to assign to the VM having the highest proportional value, right? Which is this VM3. And in this case, VM3 here have the minimum value, right? This is 1 over 100, 1 over 200, this is 1 over 300. This is the minimum value. So that's why we choose the minimum one, because by choosing this minimum one, we actually try to fulfill the maximum proportional value of that VM. Okay, so that's why we choose always the minimum value of the tag. Okay, we will see the illustrations of how this queue request here will be processed by the system. Okay, in the illustration one here, there is a request from VM that R is not satisfied yet. Okay, and from the previous algorithm, we know that we will try to process a request from a VM that the reservation is not satisfied yet. And we can see here, we have request 2, request 1, request 3, and request 4. This is the current time. We can see we have this request 2 that the value of reservation is still lower than the current time. So it means that the reservation value is not satisfied yet. We will try to process this. Okay. Oops. Okay. Okay, process this. And then for the next case, which is illustration 2 here, all our tags are already satisfied. Yeah, this is the current time. There is no tag value here. So all VM already satisfied for the reservation value for the lower bound, the minimum requirement. In this case, we will do wake-based phase here. And in this wake-based phase, we will try to exclude first a VM that already goes beyond the limit value, beyond the upper bound, which is the request 4, because the request 4 already above the current time of the clock of the limit here. Okay, and in this case we will choose a request whose proportion text is the minimum, which is the request 1 here. Okay, so we'll process this request 1. Okay, we'll process this one. Okay, and let's go next for the illustration 3. In this illustration 3, all our tags also already satisfied. There is no tag here lower than this current time. Okay, and again we exclude this request 4 because it's already above the limit, and the only remaining request is the request 3, so we will process this request 3 here. Okay, next for the illustration 4, all our tags are also already satisfied here. There is no request here. And then as we process all the requests, the current time of the clock also increase, right? Okay, and in this case, the request 4 of the limit tag value here is already lower than the current time of the clock of this limit. So it means that the limit value is not satisfied yet, so that we can process that request. Okay, so we can process this request, and that's all. We already process all, and by doing this, we can guarantee that this mClock will satisfy the reservation, which is the minimum requirement, the lower bound, and also guarantee this proportional share value. Okay, and also guarantee the limit, which is the upper bound. Okay, this is the illustration how this mClock algorithm works. Okay, we already talked about this part, the second component. The third component we also already talked, and then we try to talk the first component, which is the special case when there is an idle VM, and then this idle VM is on again. Becomes on again. Okay, this is for instance VM2 becomes active again from idle. Okay, and based on this pseudocode, we will assign by using this formula. Okay, we will assign Vm2 of the P equals to the maximum, and the maximum will be T here because there is no request, so there is no increment here. Okay, this first term will be small. Okay, so the maximum, it will choose this T value here. Okay, so what is the consequence? The consequence is based on the algorithm we already discussed in the previous slide, that we always choose a request with the minimum of the value of this tag value, right? So we will always process this request from VM2, okay, until long time of period it will increase by using this gap increment interval here. For example, until here VM2, and then it can compute fairly between VM2, VM3, and VM1 here. But in that long time, this VM3 and also VM1 will get starvations. Okay, so how this algorithm can solve this issue? Okay, I need to wait. I'm sorry, I need to clear this pen marking first. So to handle this, we can do this adjustment in this part. Okay, so instead of only assign this time here, we use this formula. This formula I rewrite here. Okay, this plus equal, equal, and then plus here. This is T from here, T. Okay, and then this 2T we can remove. We will have this minimum tag, and the minimum tag here is VM3. So we will assign VM2 the P value of VM2 will be the minimum, which is the P value of VM3 here. In this case, this 3 VM can compete fairly. Okay, so this is how this algorithm can solve this idle and then become active again case. Okay, I think that's all for this second video. We already talked about how this algorithm works in detail. In the next video, we will try to talk the specific issues, and also we will see the experimental result. Okay, and see you in the next video.